Hey class, welcome back. Today we're going to discuss concavity and the second derivative test. Concavity is referred to a special type of behavior found in the function, and I can say that it looks like a cave, right? Concave, concavity, concave. So it looks like a cave, right? Like an opening of the cave. And so you have two types of behaviors from a function. You can see concave up, concave down. That's right here, and concave up. So anything of this form. Now, what about the second derivative test? Second derivative test is referred back to something that we already discussed, first derivative test, right? So it seems like you have first derivative test and then you have second derivative test. So there has to be always a first derivative test that it's referring to. So it's actually, what this is trying to say is that you're able to find the same information from the second that you found. You can get the same information that you have found in the first derivative test by using the second derivative test. Okay, you're thinking, okay, why do we have the two different tests that will give us the same information? It's because you guys will see that sometimes one test is much easier to use than the other one, right? So the objectives for this section will be to determine intervals on which the function is concave up or concave down. Find any points of inflection of the graph of a function, which will define what does it mean to be an inflection, and then apply the second derivative test to find relative extrema of a function, right? And that's why we use the first derivative test anyways, to find the relative extrema. So what is a concave concavity? Concavity, as I described before, is a behavior of the function for which the function is behaving in a special way, concave down or concave up. Now, how do we determine this? We can determine this by looking at the behavior of the function. So let's just real quick. I won't spend too much time here because the application is much simpler than this. So if you guys notice, this is the original function. So this function is f of x. This is f of x, y equals f of x, right? But the blue line right here, the blue line happens to be the slope, the derivative, right, at every single point, right? The slope here, and the slope there. So what happens to the slope? Well, you guys notice here, the slope here it seems to be almost horizontal, right? So it's almost flat, right? Here is almost flat. Here is a little steeper, and this is steep, right? The steepest, right? Or steeper than the other one. Steeper and steeper and steeper. So what happens is that this is obviously negative because it has the slope is becoming almost zero, but it's a very small slope. So you can think about this being a fractional of a slope. But then here, let's say that this is the slope of let's say negative 1/2. But then this one becomes a little more steeper. We can say that slope, maybe this is a slope of 1. But this becomes even bigger. So the slope is, let's say this is the slope of 2, right? So what I'm saying here is that that not even just we know that the derivative is changing, right? That is going from negative and then becoming positive. But what we also know is that there is a rate of change, right? The change for the rate for which the derivative is changing, is also changing. And that is what I'm trying to say is that is becoming from negative 1/2, a fraction, to becoming a fraction, to becoming 1, to becoming 2, right? So the derivative is also changing. So if the derivative is changing, right? If you take the derivative of the derivative, I meant here x. If you take the derivative of the derivative, what do we get? The second derivative. So if you guys notice, what is happening to this is the rate of this derivative is getting from being negative to becoming positive and becoming greater positive, right? So it's changing and it's becoming it has a positive change, right? It has a positive change because it's sort of becoming greater, and that's the point. So whenever that's the idea, right? Whenever you have something of this form, this happens because your second derivative is positive. in a similar argument, we can say that this would happen, and this will be the case where your second derivative, it has an it's negative. So that means the derivative is decreasing. And that's it, right? So we're able to relate this concavity to the second derivative. And so let me just read this real quick for you guys. Let f be differentiable on an open interval I. If the graph f is concave upward on I, then the graph of f lies above all of its tangent lines. Let f be differentiable on an open interval I. The graph of f concave downward on I, then the graph of f lies below on the tangent line of I. So we see how the graph lies always below these tangent lines. Anyways, the definition of concavity says that if f is a differentiable on an open interval I, the graph of f is concave up on I when f is increasing on the interval, and concave downward when f is decreasing on that interval, which means that it tells you something about the second derivative. So here we can see that the behavior of the graph has a concave downward, right? It has a concave downward, right? It's a concave downward, so it looks like a cave down. And then it has a concave upward follow over here. But if you guys notice, there's a point where that changes. Anyways, but we'll talk about that point in a second. If you guys notice, the derivative of this is positive, right? The derivative of this is positive, and then the derivative of this is negative. It's positive, but it's decreasing, right? It's very steep here, less steeper, meaning less steeper means less, the slope is becoming smaller, right? Less steeper is smaller, the slope is smaller until it becomes 0, and it becomes negative, and the magnitude of this negative becomes steeper and steeper. So we can see here that it would be sort of the derivative is positive, but it becoming smaller and smaller until it becomes 0, and then becomes negative. But we can see here that the derivative of this is going to be negative, right? It's a negative derivative. So whenever the derivative of the derivative is negative, that means you're having a concave downward. Let me say that again. When the derivative of the derivative is negative, right, because it's decreasing, the derivative is decreasing here. When the derivative function is decreasing, that means you're having a concave downward in the original function. So that means that when your second derivative is less than 0, you have a concave down. When f prime is increasing, which means f double prime is greater than 0, you have a concave up, right? And that's the key. This is what you need to remember, and I sort of summarized it in the next line, in the next theorem. To test for concavity, let f be a function whose second derivative exists on an open interval. Obviously, we just gotta say that. If the second derivative is greater than 0 for all x in this specific interval, then the graph of f is concave upward for that specific interval. So, kind of makes sense, right? It's kind of neat. If you your second derivative is positive, then you're up, right? Up is positive, right? Another way we can think about it is like your second derivative is positive, your function is concave up. If you guys notice, what does this look like? Like a happy face, right? Let's see if that makes sense for the other one. So if the second derivative is negative, then your original function will be concave downward. What does that mean? What does that look like? Like a sad face, right? So positive second derivative, happy face, concave up. Sad, negative double derivative, that means concave downward, sad face, right? So I hope you guys that makes sense, right? I hope that makes sense. Just remember that picture because we're gonna be using that a lot in this section. So here we go. So we're gonna follow this test and to show the concavity of the following function. So determine an open interval on which the graph of the function is concave upward and concave downward. Now we notice something special, right? We noted that the second derivative has to go, if you guys notice, this is key, has to go from negative to positive. So eventually it has to pass from a 0 second derivative. So this is how we're going to be able to do this, like sort of almost the same way we did it for the first derivative. We're going to do that the same. We're going to find when the second derivative is 0, also when the second derivative is undefined, and that will help us subdivide the number line so that we can create these subintervals. Let me say that again. We're going to find when the second derivative is 0 or undefined. This will allow us to break the number line into regions, and then we can test where the second derivative is positive or negative. And so here we go. So yes, we have to go all the way to the second derivative. So we have 6 over x squared plus 3. So first thing I'm going to do is I'm going to rewrite it by moving this to the numerator, so I have a negative power. And then we're going to do the first derivative of this will be using chain rule, bring down the power, multiply by 6, gives you negative 6, leave the inside the same, subtract 1, gives you negative 2, and then multiply by the derivative of the inside. Followed by moving this to the multiplying these together, the negative 6 and 2x gives you negative 12x. Move this to the denominator, and now you have the first derivative. Now that you have this, now let's go ahead and find the second derivative. I prefer to use the quotient rule rather than using the product rule, because it's going to make my end result much easier to work with. So let's take the derivative of the derivative by using the quotient rule. So it'll be low d high minus high d low, square the bottom, and there you go. What's the square of the square? Is the fourth power. This stays the same. Derivative of this is negative 12. This stays the same. The derivative of this, we're going to have to use chain rule. So it'll be 2 times the inside, subtract 1, multiply by the derivative of the inside, and that gives us that. Then what we're going to do here is we're going to try to simplify this as much as we can. So I recognize that these two terms, that term and this term, both have x squared plus 3 as a common factor. And they also have a 12 as a common factor. So what I'm going to do is I'm going to factor the 12, and I'm going to factor the x squared plus 3, at least one, right? So factor the 12, x squared plus 3. What's left behind? Well, if you factor out an x squared plus 3, you're going to remove one of these, right? So you're left with one of them. You remove the 12, so that you're left with negative 1, followed by the plus. You factor the 12, and you factor this one out as well. So what's left behind? X, 2, 2, and x. So that gives you 4x. Distribute the negative in here. That will give us negative x squared minus 3. And then you still have this over here, which we guys notice this is for the denominator part, I ended up factoring the x squared plus 3, at least one of them. So you're going to be left with x squared plus 3 to the third here, right? Because the next line will be to sort of cancel those two. And then simplify as much as we can in here. So negative x squared is that one, negative 3 is that one, plus 4x square. I'm missing my square here. And that will give us negative 3 x squared by combining those two, and I'm sorry, positive 3x squared, and then minus 3 in there, and you still have the 12 there, and then you have this denominator. So we can see here that we can factor a 3 from those two as well. So a 3 factor a 3 from here will give us 3 times 12 will give us 36. We left with the difference of x squared and 1 all over that, and then that's our second derivative. So what are we going to do? We're going to find out the zeros of the derivative and wherever this is undefined. And this is very similar to what we've done before. So when will the second derivative be 0? Well, that means will happen whenever the numerator is 0. So we'll take the numerator and we set it equal to 0, solve for x. We know that this is going to happen whenever x squared minus 1 is equal to 0, which would be at 1. Take this, use the square root property, and that will give us these two options. When would this be undefined? Well, you're going to take the denominator and you're going to set it equal to 0. Now we know that this can never equal 0. Why? Because this is a positive number, and we know x squared is a positive number. So if you add positive plus positive, that would never cancel each other out. They're always going to be above 0. So therefore, this is never going to be 0. All right. So there's no critical numbers here. There's no critical numbers here, but there is they're not called critical numbers. There we don't have those. We didn't find anything from here, so we only have -1 and 1. So that will be useful for us to help us subdivide the number line. So just like before, but instead of having first derivative here, we're going to have second derivative there. So whenever x equals -1, the second derivative is 0. When x equals 1, the second derivative is 0. So it's important for us to make those notes for us to remind ourselves. Then we're going to test a number on the left side of -1, a number between -1 and 1, and a number on the right side of 1. And so I rewrote here the second derivative, and I made myself a note. I know that the denominator would never equal 0. Would never equal negative because it's always positive. So I wrote myself a positive note. 36 is always going to be positive. So there you go. That's always positive. So everything that we're going to test will depend from here. So when I plug in -2, again, we're only looking whether this is positive or negative, right? We're only looking whether this is positive or negative. That's the beauty of this. Do not overthink this. Do not overdo this problem. We don't want to know exactly what this is equal to. We only care whether this is positive or negative. Positive or negative, because that gives us all the information that we need. Okay, so here we go. When you plug in -2, we know that we already decided that that's going to be a positive, that's going to be a positive, but here you're going to get a 4 minus 1, which gives you positive. So positive or positive is positive. When you plug in 0, we already said that this is going to be a positive, this is going to be a positive, but when you plug in a 0 in here, that will give you a negative number. So that gives you negative over positive, it's negative. Then we have positive over positive. When you plug in 2, that also going to give you a positive, so that's going to give you a positive. So what do we have? So we have positive here, negative for this interval, and then positive for this interval. So therefore, what does that tell you about the original function? What we said that when you have positive second derivative, it gives you a happy face. When you get a second derivative negative, gives you a sad face. Positive gives you positive happy face. So we know that the function is concave upward from -infinity to -1, from 1 to infinity, and concave down from -1 to 1. And that's it. So if you guys see here the picture, we can kind of confirm that this is half of the concave up. Here is the concave up, concave down right here, and then this is a concave up. So there you go, right? So it's kind of neat, right, that we are able to sort of know more about the behavior of the function by looking at this, by looking at the second derivative. That's sort of the point of this section. All right, so we do have to check wherever the second derivative is 0 and where the second derivative does not exist. So here's a problem for you guys to work later, and you guys can kind of confirm that information. All right, so if you guys noticed, there was a particular point that was sort of interesting that we describe up top. Do you guys notice that there was a point where the function changed from concave up to concave down? That was sort of a big deal. That's actually giving us information, a lot of information about the problem. So because it's a big type of it's a big deal problem information, we're actually going to give them a name. That's known as the point of inflection. So the point where it changes from concave up to concave down, that's the point of inflection. Where it changes from concave down to concave up, that's the point of inflection. Concave up to concave down, that's point of inflection. So we have, anytime there is a change of concavity, that point is an inflection point. But it is very specific. It's not just whenever the derivative is 0, the second derivative is 0 or does not exist. It is actually very specific. You must change concavity to be able to actually have an inflection. Because if you have concave up followed by concave up, then that's not a point of inflection, right? Or if you have concave down, change to concave down, again, you didn't change concavity, you still maintain the same concavity. So you must have a change of concavity. All right, so the definition is let f be a function that is continuous in an open interval, and let c be a point on the interval. If the graph of f has a tangent line at this point, then this point is a point of inflection of the graph f when the concavity of f changes from upward to downward or downward to upward at that point. Points of inflection. If c of f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime does not exist at c. Vice versa, this statement does not go backwards, right? If you have these two, that does not mean automatically that that's an inflection point. All right. All right, so let's try the next example. Let's determine the points of inflection and discuss the concavity of the graph of the following function. Okay, so we already know how to find concavity. Now, what we're doing differently here is we're also finding the point of inflection. Now, the point of inflection has to be a point, so therefore you have to have the x component and the y component. So let's begin. What are we going to do first? First, find the second derivative of the function. So we have x to the fourth minus 4x cubed. So the derivative of this will be a 4x cubed minus 12x squared. The derivative of the derivative will be 12x squared minus 24x. And then naturally we always try to factor this out because this will help us find these much easier. So factor the 12x from this expression, and this will is going to leave us with x minus 2. Now we're going to try both of them, but we notice that this is not going to work. This is not going to happen for the second derivative because this is a polynomial, and polynomials are defined everywhere. So this is not going to be undefined anywhere. So there's no possible inflections from here. So what about the second part, the second derivative equal to 0? Well, in that case, if we set this equal to 0, we have two options, x equals 0, or we have x minus 2 equals 0. Do you see how the benefit of factoring it out was? By factoring out, it was much easier for us to find these zeros. This suggests that x equals 2. So this suggests that x equals 0, x equals 2 will subdivide the number line. And these are the possible inflection points, right? The possible because they're not confirmed them to be. We haven't confirmed that those are they're going to be where the inflection point will be, but we know that this will separate our number line. So we're going to separate our number line, x equals 0, x equals 2. Number line for the second derivative. You guys notice second derivative because we're talking about concavity. Here the second derivative will be 0 and the second derivative will be 0. So we're going to test a point on the left side, a point in the middle, a number on the right side. So here's my second derivative. I'd rather have it in the factor form because it makes it easier for me to compute the signs, right? Again, we only care for the signs. We don't care about the actual number. So do not overdo this problem. X equals negative 1. Plugging negative 1 into the second derivative. This will give you a negative number, right? 12 negative, and negative 1, negative 2. So this is positive, this is negative, and this is going to be negative. So positive times negative gives you positive. Now plugging 1. That will be 12, 1, 1 minus 2. This is positive, positive, positive. Then this is negative. So positive times negative will give you negative. What about 3? You have 12 times 3 times 3 minus 2. This will be positive, this will be positive, this will be positive. Positive times positive will be positive. So therefore, we have positive, negative, positive. Now, what does that tell you about the function? Well, whenever this is positive, second derivative is positive, we have a happy face. Whenever the second derivative is negative, we have a sad face. So therefore, we have concave up from negative infinity to 0 and from 2 to infinity. We have concave down from 0 to 2. And now we have to find the inflection. To find the inflection point, we need to do is plug in 0 and 2 into the original function to find the y component of this x value. Remember the y component of this function is found from the function. So plug in 0 to the original function, and I did, and I got 0. Plug in 2 to the original function, and I got negative 16. So the inflection, and these are inflection because we do have a change of concavity. We went from concave up to concave down. So that means that this is the inflection point at 0, 0. And this is an inflection point because we also changed concavity from from concave down to concave up. So negative 16 is the inflection point. And you guys can kind of see here, right? Concave up, change in inflection, concave down. Change in inflection point, concave up. And there you go, right? All right. So there'll be cases where, again, like one thing looks like an inflection, but it might not be an inflection, right? So we do have to test them. Okay, so we'll see this more. We have a few examples like that in the homework, and we're gonna see this in another chapter in section 3.6. So this will be essential for us to be able to graph a function, right? When we start graphing and sketching a graph later on in 3.6, we're gonna be using that information a lot. Okay, so second derivative test. Why we're doing this? We're trying to find the relative extrema and relative minima. So we already know that we know how to find it using the first derivative test. Now what we're going to do is we're going to use the second derivative test. So this is the concept right here. So we know that if this is the function, right? This is your f, right? We know that this is a relative min. Now, if you guys notice, what happens? What's so important about relative min here? How do we relate this relative min to the second derivative? Well, we know that second derivative talks about concavity. So what if you already know that this gives you a critical number? So you already know that this is either a relative max or relative min, right? Let's pretend that you know that this is a relative max or relative min. You don't know which one it is. But what about if I gave you that this, in addition to be a relative critical number, it's located on a concave up? Well, if it's in a concave up, then this is in part of the behavior of the graph where it looks like a happy face. So because we already know that this is supposed to be a concave, it's a critical number, then this means that this had to be a relative min, because that way it satisfies this curve, right? This concave up curve. In a similar way, if this is a critical number and you know it's in a concave downward, then it automatically you know that this has to be the top of the hill, right? Top of the hill, because it belongs in a concave downward. So this is in a valley, and this is in the top of the hill. So do you guys see how that connects, right? So that's the connection here. So if you know that C, you have a critical number, in addition you know that it's the second derivative, then that means it's a relative min. If you know that this is a critical number and you know it's in a concave, the second derivative is less than 0, then you know this is a relative max. And that's it. That's the second derivative test. Now, if the second derivative happens to be if you get the second derivative and that's 0, then the test fails, and the test didn't help out. So you can use the first derivative test for that instead. Let me say that again. If you don't get positive or negative, instead you get a 0, then the test does not work. So therefore you have to use the first derivative test. All right. So using the second derivative test, find the extrema of the function. Now, in the test, I will ask you, I promise you, I will ask you to, at some point or another, to do to find the relative max and relative min. One problem by doing using the first derivative test, and then another one by using the second derivative test. So you will have to know both of them. You do need to know both of them, and they're pretty straightforward. They're pretty straightforward. They're not. Let's not overthink the problem. So how are we going to do this? First, you need to know the critical number. So first, find the derivative of the function. So this is the function. Take the derivative. That gives you negative 15x to the 4 plus 15x squared. Then find the critical numbers. You know how to find those. We've done this 100 times already. set it equal to 0, or whenever this is undefined. This is not going to be possible because it is a polynomial, and this polynomial cannot be undefined, right? Because it's a polynomial. The first derivative, we're going to first factor out as much as we can. So we factor negative 15x squared. We're left with x squared minus 1. This suggests that this is going to give us one of the zeros, and this suggests this is going to give us the other 0. So by solving for this will give us plus or minus 1, and this will give us 0. So we have 3 critical numbers. Now what we're going to do is we're going to take the second derivative, and we're going to test those numbers in the second derivative. So let's go ahead and do that. So take the second derivative of this right here. Where is it at? Right there. So this will give us negative 60 x cubed, and this will give us plus 30x. Factor as much as you can, so we can factor negative 30x, and this gives us with 2x squared minus 1. And what we're going to do is we're going to test our critical numbers. We're going to test our critical numbers into the second derivative. So let's do that. So when you plug in x equals 0 into the second derivative, what do we get? We get 0, right? We get 0. So that's inconclusive. So we're going to have to use the first derivative for this test for that. For x1 and negative 1, when you plug in 1 and negative 1 into the second derivative, we end up getting negative, positive, positive, which is negative, which is less than 0, which is this suggests it's going to be a max. This is going to be, when you plug in negative 1, you're going to get negative, negative, positive, and this will give us a positive, which is greater than 0, which suggests this is going to be a min. Okay, so let me say this a few things, right? This is how I remember which one is which, because we can easily confuse them. This is how I remember. So if you have a if you have less than 0, that means you have a concave down. I only remember that. I have to remember that this is a concave down, and so I can see this in my head, and so therefore this needs to be a max. If this is a greater than 0, then I know this is a concave up, so therefore this is going to give me a value, right? So that's how I remember. I don't memorize, oh, when it's less than 0, the second derivative, this will give you max. No, I try not to memorize too many things. I just use the concept and try to remember the concept by itself. All right. So, but then we're not done, because we need to check what happens with this one. So we're gonna have to use the first derivative to be able to find what happens to that one. So we have to work a little harder to find the second one. Now, if you guys notice, we would have been done like much quicker doing this with the second derivative than doing the first derivative, because we wouldn't have to test any numbers or as many numbers as we do here. If you guys think about that, the logic makes sense to use the second derivative test most of the time, because it's much quicker. I mean, obviously, if the second derivative is not too hard to find. All right, so let's finish this problem. So for this part, we're gonna go ahead and look at the first derivative and test x equals 0. Now we gotta test numbers. We have to use numbers that we're gonna test that are between negative 1 and 0 and 0 and 1. So I use negative 1/2 and 1/2. So I test them on the first derivative, and then I got them positive, and I got positive. So therefore this is positive and this is positive. So this suggests that this is not a relative extrema, because we're not changing signs. So no relative extrema at x equals 0. All right. So what about how can we find this extrema now? Excuse me. Well, we already know that when x equals 1, we can find the actual y value, the actual point. At x equals 1, plug it into the original function, and that will give us the y component, which is 2. Plugging negative 1 into the original function, that gives us negative 2. And then here 0 will just give us one of the inflection points, but that's not a relative max nor a relative min. Anyways, so we found the relative extrema for both one, negative 1, negative 2, 1, positive 2. And there you go, right? So do you see how we were able to find this extrema using this second derivative? There's not much I can add here. but for only you guys to practice this process, right? Obviously it changes depending on the algebra depends on the actual function, but other than that the concept is the same. So find critical numbers, and then once you find the critical numbers, then you find the second derivative and use those critical numbers to test them in the second derivative just by plugging them in, and just check whether they're positive or negative. If they're positive, if your second derivative is positive, then that's a relative min. It is, if it's negative, then you have a relative max. There you go. All right, hopefully this is helpful. I'll see you guys next time.